Hey guys, so just making a quick video here on some of the homework problems from this section's homework. Just because these are kind of some tough scenarios, and I wanted to make sure these were kind of clear as to how this process works. So as as we're looking at our setup for 25 here, we're looking at the limit as x approaches negative infinity, right? So our goal on this is to simplify this in such a way that we can use some of our basic knowledge in order to get rid of x is kind of the goal, right? And only have numbers left over. Ultimately, here's kind of what we're looking for. When you talk about 1 over x, if you're approaching infinity, whether it's positive or negative, right, we know that 1 over x is 0, right? Because, and that's what I put in the little side note down here, right? Because if you have a fraction, if that bottom number is getting bigger and bigger and bigger and bigger, we know the overall value of that fraction gets smaller. So it approaches 0. So that's the way we're going to be able to get rid of this in order to just get a number answer out of this. So here we go. So one of the techniques that we're learning on this is I basically can divide all of my terms by something that would reduce them or simplify them. Okay, and so in this case, we're going to divide everything by x, because that's really our largest exponent. As I look at this, we know that the square root of x squared is just x. And so that's what we're going to do. We're going to divide everything by x. So I divided the numerator by x, and I'm dividing the denominator by negative x squared, and the square root of x squared. And this is what I wanted to explain. So if you look at this right here, okay, we know that the square root of x squared could equal either positive or negative x, right? It could be a positive or a negative because both those fit if you plug it back in. So how do we know if we should use this as like a negative value or as a positive value? Well, if we're headed towards negative infinity, right, then we're representing a negative number out of this because we're going to further and further to the left, right? So if we're approaching negative infinity, right, that's when we want to use the negative version of this because it represents x is less than 0. So if you look at the denominator portion of this, we're going to divide these by negative square root of x squared, which is really like dividing by negative x, right, when we look at this. But what we're really saying is we know that the outcome of this needs to represent a negative value because we're approaching negative infinity. It's got to approach a negative value. So let's simplify some of this. So if I have x over x on top, obviously that's just 1. If I divide each of those terms by negative square root of x squared, well, these guys would reduce to just 1. I still got the negative out front. Right? These guys would reduce to just 1, and then x over x squared becomes 1 over x. And so that's where we get to this point right here. Typically on this, it doesn't matter if you put the negative on bottom or on top. Oftentimes our book puts it on top. So I just wanted to show you where this negative is coming from, right? It's coming from here. So, but whether you put it here or here really doesn't matter. It's not going to change our answer. Anyway, so this is the point where we can recognize that 1 over x becomes 0 as we approach negative infinity, right? Because this number becomes so infinitely small that it's worth nothing, right? And so really we can take that out of the equation and look at it as just this. And so now if I simplify that, I get negative 1. So let me show you this similar idea here with number 27. So you can kind of see it again. So really the same issue is going to apply because x is approaching negative infinity, right? And so here's what we're starting with. And so to simplify this, again, I'm going to divide everything by x. But for x's less than 0, right, I know the result of that needs to be a negative result. So as I look under the radical here, if you look at each one of these as kind of individuals, so the square root of x squared is really just x, right? But because I'm approaching negative infinity, I know it needs to represent a negative value. And so we have to throw the negative in there in order to make this make sense and to fit our math rules, right? So Essentially, we're dividing everything by x. However, we're putting it in this notation in order to help us simplify the denominator. So we're really dividing the top and the bottom by x. So if I divide each of the top pieces by x, it's going to look like this. And if I divide the bottom by x, it's going to look like this, right? But again, we're putting it in that notation because we're approaching negative infinity, and this needs to represent a negative value. All right, so if we simplify that, the numerator cleans up pretty nice. The denominator, again, x squared over x squared is 1. And x over x squared is 1 over x. So this is the point where now we can look at both of these 1 over x's and say, hey, as we're approaching negative infinity, so as x approaches negative infinity, this fraction is approaching 0. So it's like it's becoming 0, right? And so these guys zero out, and this is all that I'm left with. And so if we simplify that, we get our limit, which is negative 2. All right, let me go down to 31. So we have kind of a similar issue on this one. It's really just different because it's written in fraction form instead of radical form. But this one is approaching positive infinity instead of negative infinity, right? So that matters. But as I look at the denominator, think of this as x to the 2/3 power, right? We know that this is a cube root. 1/3 power is a cube root of x squared, right? And so if we put those guys together, you guys know that a power raised to a power, you multiply them, so it becomes x to the 2/3 power. So what we're going to do is we're going to divide all of our terms by x to the 2/3 power. So I divided, as you can see right here, every single term by x to the 2/3 power, and then from here I'm just going to simplify. If you look at this one, remember in division we subtract the exponents. So think of this as x to the first. So I'm doing 1 minus 2/3 to get this. This one I'm just leaving alone for now. On bottom, again, kind of doing that same idea with each of these individually. This is already x. This is already x to the 2/3. So this divided by itself is just 1. And then this one, 1 to the 1/3 power is still 1. So we're just putting it as 1 over x to the 2/3. So it looks like this. So this still goes back to that same idea that if x is approaching infinity, that's still making my denominator larger and larger and larger and larger, which makes this fraction get smaller and smaller, right? So again, it's becoming 0. So if these guys zero out, this is all I am left with, which in this case means that the limit does not exist, right? Because if x is approaching infinity, then the result of this is also approaching infinity, and we don't use infinity as a limit unless it's a one-sided limit. This is not a one-sided limit. This is like a both-sided limit, right? So that's why we're going to say it does not exist. All right, let me take you down to 35. 35 was very tricky. I had to kind of go through this and really make sense of the explanation on this, but let me see if I can kind of talk you through it. So as we look at this, they're essentially going to use the squeeze theorem here in order to figure out the limit, because it was kind of like they couldn't really get the limit of this using any of our basic rules. So what they said was, well, let's just look at the sort of like the domain of this problem, right? With a sine function, remember this is your sine functions work up and down. They represent the y values, right? A sine function goes between -1 and +1. All right, that's what sine functions do. So right here, I kind of stated the domain that sine function is kind of stuck between -1 and +1. So if you just looked at the numerator, that's what this is, right? This is the numerator of this idea, right? It's the numerator has to be between -1 and 1. From there, then we can just throw in the x on bottom, right? So I got my x on bottom, so we're going to do that consistently through the entire domain. because it's just like basically whatever you do to one item within the equation, you have to do it to all sides of the equation, right? So if I'm going to take this middle term and divide it by x, then I'm going to divide everything by x, right? And so here's the setup that we end up with. So the way this worked out is the limit of this is between the limit of negative 1 over x and positive 1 over x, right? It has to be between those two functions. Well, the limit of both of those is 0. And if you graph this, it's great. You should definitely check out the graph. Graph all three of these. It's kind of an interesting graph, but it's a really clear picture as to why this is approaching 0, right? Because if you look at the graph, it shows you that this guy approaches 0, this approaches 0, and since this is between them, by the squeeze theorem, he's also approaching 0. So we could certainly do that without graphing it, but the graph is a great visual. So just remember, as this approaches infinity, right, when x is on bottom, it makes this whole fraction approach 0. So we know he's approaching 0, we know he's approaching 0, and again, since he's between them by the squeeze theorem, he's approaching 0 as well. All right, let's look at 37. 37 is just easier if you rewrite it without the negative exponent. So remember, negative exponents just mean fractions. So, or reciprocal, I should say. So I took the e to the x and put it on bottom, right? So I could look at it this way. So I just rewrote it into something that looked a little more familiar. But now we're going back to that idea of so as x gets bigger and bigger and bigger, so as x approaches infinity, what is happening to this fraction? As x approaches infinity, my denominator is getting larger and larger and larger, which makes the fraction, again, get smaller and smaller and smaller. So we know this fraction is approaching 0 as x approaches infinity, and that's what I wrote right here, which means this can now basically turn into 0, right? And that's where you get this right here. And so you're left with just a constant, which is 2. Let's look at 39. So for 39, I really took a similar approach on this one. So if we said, what is the log of 1 plus 1 over 10 to the x power, then I have that 10 over x fraction. So as you can see down here, we're running into that same issue. With x on bottom, as x gets larger, as x approaches infinity, then this fraction gets smaller and approaches 0. So that allows him to 0 out, and I'm left with just this right here. Right? And remember the way that we interpret a log. The base, the way we would read this is 10 to what power is 1. And we know 10 to the 0 power is 1, right? So the log of 1 is 0. So there we are, our x's are gone, we're left with just our constant, which is then our limit. All right, let me show you 2 more. Oh, 3 more. I couldn't remember how many I had on here. On 41, you have to go back to the idea of an inverse trig function. So I threw in some graphs here to remind you of something. We just haven't looked at this in a long time. We covered this in the first semester, but it's really been a long time. So as you look at just this first part, 8 over t, it is for the same reason that we've talked about before, right down here. 8 over t is approaching 0 as t approaches infinity. Okay, so hopefully that's something that we get by now. So this first term can 0 out, which is why you have a 0 right here. But the trick on this one is, what are we approaching here, right? So as t approaches infinity, what is the inverse tangent function approaching? So I think the easiest way to look at this is by looking at the graph. Remember, this is our parent function for a tangent graph. So if you look at this one, you got your domain goes from negative pi over 2 to positive pi over 2. Your range, right, is infinite on this guy. So that's the tangent graph. So what happens to this graph when we take its inverse? Remember, an inverse is where everything switches. Your x and your y switches. So your domain and your range switches. So the domain that did go from negative pi over 2 to positive pi over 2, that's now the range. Goes from negative pi over 2 to positive pi over 2. Right? So for the inverse tangent function, right, that's now the maximum point. The domain can go on forever. So the domain can approach, x can approach infinity. right? So as t approaches infinity, or in other words, as you go to the right, what is your graph approaching? And you can see as we move to the right that our graph is approaching pi over 2. Right, so that's like our largest tangent value here. So that's what the graph is approaching, so that's why I can now sub that out with pi over 2. And then 0 minus pi over 2 would just be negative pi over 2. So it really helps to have an understanding of this graphically, I think, to make sense of why this is approaching pi over 2. 45, they gave us this graph, and they asked about horizontal asymptotes. So if we graph this, so I think this was one they didn't graph for us. I think I graphed it in Desmos, and then I drew this out here. So if you do take a look at the graph, which they said to do, you can now see that the right side is clearly approaching positive 1, which means we have a horizontal asymptote at x equals 1. And the left side of this graph is approaching negative 1. So as x approaches negative infinity, our function is approaching negative 1. So that means we have a horizontal asymptote at x equals negative 1. So those are our two horizontal asymptotes. Let's go to 53. I think this is our last one here. So on 53, this one went back to the idea of multiplying by a conjugate. Because otherwise there just wasn't anything that really fit our rules in here. Nothing really fit the rules that we had to work with. There were no fractions, no way to get rid of x within that scenario right there. So we have to sort of rework it to put it into a different format. So what I did on this one was multiply it by its conjugate, top and bottom, right? And that put me here. If you clean up the top, comes down to just be x. And now it goes right back into those first couple problems that we looked at, right? Essentially at this point, I'm going to divide everything by x. But because this isn't just seen as x, this is the square root of x squared, which again, that's still x, but we need to understand that if we are approaching negative infinity like this one is, right, that when I divide this, it needs to represent a negative value. Okay, and so again, when we get to these terms, instead of saying I'm going to divide by x, we're going to do what we talked about earlier, right, which is x is going to represent negative square root of x squared for all x is less than 0. And that's what these guys represent because we're approaching negative infinity. Right, so I went through and did the same trick that I did before. I divided this one by x. I divided this one by x. I divided these by this guy. So if you simplify all that, here's the look that we were going for. And now at this point, again, the 1 over x can zero out because we're approaching infinity, negative infinity. And so I'm left with just this. And that cleans up nicely to just 1/6. So I hope that helps. That's it for this one.